We're going to take a look at our first problem, which involves the use of the Pythagorean theorem. Now remember, the Pythagorean theorem gives us a relationship of the sides of a right triangle. Let's read our problem. Find the length of the hypotenuse of a right triangle with legs of 9 and 12 centimeters. When approaching a problem like this that involves a particular geometric shape, it's probably best to sketch a little drawing. So we're going to sketch ourselves a little drawing of a right triangle. Now remember, a right triangle is a triangle with exactly one right angle. The little box in the corner denotes the 90 degree or the right angle. Now, in this particular problem, it says the length of the hypotenuse is what we want to find. Now remember, in the right triangle, the longest side is considered the hypotenuse. Now, you may say, well, I don't know if this one's longer at the bottom or this one going diagonally is longer. Well, here's a hint. The 90 degree angle or the right angle is always the largest angle in the triangle. The reason being is because the angle sum of any triangle is 180 degrees. This angle is taking 90 degrees of that 180, which leaves these two to add up to 90 degrees. So there's no way that either of these two could be 90 or more. So what we can say is this: if we know this is the right angle, and this is indeed the largest angle of the triangle, the side opposite the largest angle is also the longest side. So we can be safe to assume that the side opposite the right angle is the hypotenuse, and we're going to label that x because we don't know that length. Now the other two are called legs, and in this problem we're given that those lengths are 9 and 12. Now just for visual effect, we're going to go ahead and make the shorter looking leg 9 and the longer looking leg 12. But again, don't go by the drawing at all times. Just go by the numbers that are given. Now Pythagoras discovered one thing that's quite interesting. Anytime you have a right triangle, the following relationship is true. The length of the hypotenuse squared is equal to the sum of the legs squared. In other words, the value here and square it, that's equal to this number squared plus this number squared. That's quite an accomplishment for a Greek mathematician. If you're interested in Pythagoras, you can find many books written about him and all of his discoveries. Now, that tells us here that x squared is equal to the sum of the legs squared. In this case, that's 9 squared plus 12 squared. And we know that 9 squared is 81. We know that 12 squared is 144. Add 81 plus 144, and that tells us that x squared is equal to 225. Now that we've gotten here, you have to ask yourself, what number times itself is 225? Well, with the use of a calculator, or if you just happen to know the fact, it turns out that 15 times 15 is 225. Now, if we were going to be real honest, we would have to also include negative 15, because 15 times negative 15 is also positive 225. So we'll show that as plus or minus, meaning it could be positive 15 or negative 15. But now, let's answer the question asked. We're looking for the length of the hypotenuse of this right triangle. Can the length of any side ever be a negative number? I don't think so. If you look at any ruler, you'll never see negative numbers. So that lets us eliminate the negative 15, and we will use only the positive value as our solution. So in this particular case, we can conclude that the hypotenuse has length of 15. In this case, we're in centimeters. So there we have it. By the way, the trio 9, 12, 15 is referred to as the Pythagorean triple. Any three numbers that fit the relationship that this one squared is equal to the sum of the other two squared is called a Pythagorean triple. Now that we've looked at Pythagoras, let's go on to some radical equations. Following, we're going to consider this next equation that involves some radicals. Now, we're going to look at the following. We have the square root of 3x minus 2 minus 7 is equal to 0. Now, as solving equations, our goal is always to isolate the variable. So even though we've got radicals involved, our goal is still to isolate that variable. Now, right now, I see that I have a radical minus the 7 is equal to 0. Since we want to eliminate or get this variable x on one side of the equation by itself, I hope you can see that at least we better start by isolating this entire term. To isolate this term, let's go ahead and add 7 to both sides of the equation. That will give us the square root of 3x minus 2 equals 7. Now, our x is stuck under that radical sign. So our goal is to get rid of that radical sign so that we can then solve for x. We do have a few tricks up our sleeves. Remember, if we have an equation, as we do in this case, we can do whatever we want to equations as long as we do the same thing to both sides of our equation. So if I square the left-hand side of the equation, all I have to do to make this a valid step is to square the other side of the equation. Now, why, you ask, am I squaring this equation? Look at the left-hand side. If I square this radical, what happens is I have the square root of 3x minus 2 times itself, and we know enough about radicals that we see it becomes simply 3x minus 2. On the right-hand side, I have 7 squared, which I know is 49. Now, to solve for 3x then, it's simple at this point. We're going to add 2 to both sides. 3x is equal to 51. Divide both sides by 3, and x equals 17. Now, there's one additional step that you need to not forget when you're working with these radical equations, and that's this. When you get your solution, as we did here, x equals 17, you must always check to make sure that your solution works. The reason being is because we're squaring here in the second step or the first step, negative sign. Because if we square a negative number, we'll get a positive. So that could create some problems for us. So what we're going to do is check to make sure that our solution makes sense. 3 times 17, which is going to give us the square root of 3 times 17 is 51, minus 2, minus 7. Is that equal to 0? If it is, then our solution is correct. If it's not equal, then we're out of luck. Then our solution is not correct. 51 minus 2, the square root of 49, minus 7, is that equal to 0? The square root of 49, 7. So we get here 7 minus 7. Is that equal to 0? Well, it certainly is. So our solution checks out. Now, why did we check? Again, the reason why you have to check all radical equations when you incorporate squaring both sides of the equation is because if we square a negative number, if we had a negative there, you would lose the sign and it would become positive. Then when you check your solution, you'll see it doesn't work. If that happens, your solution is no solution if that's the only one you came up with. So again, how do we solve these radical equations? Step one, we want to isolate the radical. We did this in this problem by adding 7 to both sides. Once we have the radical on one side of the equation all by itself, we square both sides of the equation. After we square both sides, we solve the resulting easier linear equation by incorporating all the rules of addition, subtraction, multiplication, and division that we learned in the past. We get our solution, x equals 17, and don't be hasty. Take the extra minute it takes to check your solution. You take your solution, substitute it back into the original equation. Here it is. Do your calculations and check to make sure you get a true solution or a true answer. A true statement is what I'm trying to say there. Okay, once you do that, then you know that your solution is a valid one. So my advice to you on this is just to work carefully and don't be hasty. Do not forget to check your final solution.